Assalamualaikum warahmatullah and very good morning to everyone. So we are going to continue with chapter 4, pure bending, and I'm going to separate this chapter into several numbers of lectures and tutorials. In this chapter, basically you are going to be introduced to bending behavior. Okay, we are going to define the deformations, strains and normal stresses in beams subject to pure bending. And later on, we are going to describe the behavior of composite beams made of more than one material. For introduction, this chapter and the followings are going to analyze the stresses and strains in prismatic members subjected to bending. Bending is a major concept used in the design of many machine and structural components such as beams and girders. In this lecture, it is devoted to the analysis of prismatic members subjected to equal and opposite couples M and M prime, acting in the same longitudinal plane. Such members are said to be in pure bending. The members are assumed to possess a plane of symmetry with the couple M and M prime acting in that plane. An example of pure bending is provided by the bar of a typical barbell as it is held overhead by a weightlifter as shown in this figure. So Behdad Salimi in 2006 Rio Olympics actually broke the record with 216 kg but unable to get any medal due to disqualification. If we look at the bar, it carries equal weight at equal distance from the hands of the weightlifter. Because of the symmetry of the free body diagram of the bar, as we can see in this figure, the reaction at the hands must be equal and opposite to the weight. Therefore, as far as the middle portion CD of the bar is concerned, the weight and the reactions can be replaced by two equal and opposite 9.6 Newton meter couples. So we should have an equals weight force at both ends, and it must be equal to the 9.6 Newton meter couples, showing that the middle portion of the bar is actually in pure bending. The result obtained from the direct application of pure bending will be used in the analysis of other types of loadings, such as eccentric axial loadings and transverse loading. So this photo shows a steel bar clamps used to exert a 600 Newton forces on a piece of on the two pieces of lumber as they are being glued together. So we have two pieces, 1, 2. In this figure, it shows the equal and opposite forces exerted by the lumber on the clamp. So we have P prime and P. These forces result in an eccentric loading of the straight portion of the clamp. So we can say that in figure at the right here, a section C prime has been passed through the clamp and a free body diagram has been drawn of the upper half of the clamp. The internal forces in the section are equivalent to a 600 Newton axial tensile force of P and a moment of 72 Newton meter of couple M. By combining our knowledge of the stresses under eccentric load and the result of an analysis stresses in pure bending, the distribution of stresses under an eccentric load is obtained. So we can say that eccentric loading is when axial loading, which does not pass through a section centroid, are going to produce internal forces equivalent to an axial force and also a couple or a moment. So the study of pure bending also plays an essential role in the study of beams subjected to various types of transverse loads. This is specifically useful for prismatic members. Consider a cantilever beam. Here we have a cantilever beam of AB supporting a concentrated load of P at its free end. And if a section is passed through C here at a distance x from A, okay, so we have distance x, and we should get a free body diagram similar to the figure here. The free body diagram of AC shows that the internal forces in the section of force P prime equal and opposite to the force P. And also we have a couple M of a magnitude M equal to Px. So we should get the moment M is equal to Px. The distribution of normal stresses in the section can be obtained from the couple M as if the beam were in pure bending. Next, we are going to learn about symmetric member in a pure bending. Let's consider we have a prismatic member AB like as shown in the figure A here, where this prismatic member AB possess a plane of symmetry and the member is subjected to equal and opposite couple of M and M prime. So we have M and M prime. So we have two couples acting in that plane. If a section is passed through the member AB at some arbitrary point C, so let's say we have this section, the condition of equilibrium of the portion AC of the member require the internal forces in the section to be equivalent to the couple M. So it must be M and M prime. The moment M of that couple is the bending moment in the section. Following the usual convention, okay, we are going to have a positive sign assigned to M when the member is bent as shown in this figure, when the concavity of the beam faces upward, and a negative signs will be assigned when we have the concavity of the beam faces downward. Denoting by sigma x the normal stress at a given point of the cross section, and by tau xy and tau xz as the components of the shearing stress, we can express that the system of the elementary internal forces exerted on the section is equivalent to the couple M. So we should have sigma x, tau xy, tau xz is actually equal, these components is actually equal to the couple M of this same section. Recall from static that a couple M actually consists of two equal and opposite forces. The sum of the components of these forces in any direction is therefore equal to zero. Selecting any arbitrary point at the z-axis shown in this figure, the equivalence of the elementary internal forces and the couple M is expressed by writing that the sums of the components and the moments of the forces are equal to the corresponding components and moments of the couple M. So we should have the components, the x components should be the integration, so it should be the integration of sigma x over the area A should be equal to 0, and the moment about y-axis should be integration of z times sigma x dA also equal to 0, while the moment about z-axis should be negative y sigma x dA, where this one should be equal to the couple M. That's it for our first lecture. We are going to continue with lecture 2 on different video.